Hey guys, this is a question from the CSES problem set, and the question is Hamiltonian flights. Here the time limit given is 1 second. So we can safely perform 10 to the power 8 operation for this case. And the memory limit is 512 MB. We can say that it's more generic. Yeah, somewhere more generic only, but we will try to be more specific to L1 cache optimized, right? So that will not get MLE in general, right? Yeah. Now the question states that there are n cities and m flight connection between them, and I want to travel from Sergala to Lamala so that I visit each city exactly once, right? Yeah. And I need to find the number of possible routes here. Okay. Yeah. Now the input format given is the first input line has two integer n and m. That is your number of cities and flights, and the cities are numbered from 1 to n. And the city 1 is your Sergala, and city n is your Lamala. So what I'm bound to go from, since I need to visit from Sergala to Lamala, so our start city will be always 1, and our n city will be always n for a specific route, right? Yeah. Now the question states that then there are m lines describing the flight, and each line has two integers a and b, and there is a flight from city A to city B, and all flights are one-way flights. Okay, so this m lines, you can say that these are describing the description of a flight going from one city A to another city B, right? Now I need to print what? I need to print the number of routes modulo 1e9 plus 7 here. Okay. And if you look at a constraint here, then n lies between 2 to 20, a very sweet spot somewhere of wood. You know, if you are aware that if n is less than or equal to 20, we can safely perform Bitmask operation because 2 to the power 20 is close to 10 to the power 6. So this will allow me to like perform the operation within in the complexity of like 2 to the power n into n, somewhere like that. Yeah. And the constraint here of m is lying between 1 to n squared, so somewhere like 1 to 400, and ab is lying between 1 to n. Fine. Now let's come to the logic part of it. So guys, if I come to the logic part of it, then what the question states that I need to like for a path to be valid, I need to start at city 1 and I need to reach city n by traveling all the cities between them exactly once. Can we say that? Yeah, this is a question telling. So if you observe, then our start city and the n city is always fixed, right? Then only our path to be valid to reach from city 1 to n. Can we say that? Yeah. So number of possible ways is basically these cities only, that is in between this in which we can arrange these cities. This will be our number of possible ways. But here the condition, if it's generic, then I can directly say that it's n factorial, right? But here it's not a generic one. It is telling that I need to visit each city exactly once, or you can say that you in the path you need to visit each node exactly once. So because of this condition, can we say that this is a example of a Hamiltonian path? What is a Hamiltonian path, guys? If you are aware, then Hamiltonian path states that the path in which like I visit each node exactly once, then that path would be considered as Hamiltonian path. It is an example of non-deterministic polynomial time, where basically if you try to calculate like the distance, or if you try to calculate the path, in general CPU will not able to do, because the complexity of it is quite higher, and because of that, if the path will grows, then we will not able to find the overall path in the standard time period. So therefore it is considered as a non-deterministic polynomial time complexity path, and that's why this is a Hamiltonian path example. Can we say that? Yeah. Now, if we try to look more here, then the question says that all flights are one-way flights. Okay, so you cannot have another flight back from one node to another, right? So it is a directed graph. Can we say that? Yeah, it is a somewhere like directed path. So directed graph, you can say, or as is here given is directed, right? And another thing that if you look at the SS, basically that is defining the flights, yeah, because it is connecting the city A to city B, or you can consider node A to node B. So if I look at the SS here, there is no weight assigned to SS, right? So since there is no weight assigned to SS, so can we say that the SS is unweighted? Yeah. So another observation we make here that since the SS is your unweighted, basically by default, if the S weight is like unweighted, we consider the weight to be 1. Okay, and that is one thing. Okay, plus the SS is directed also. That is another thing. So yeah, you are not visiting every neighbor again. Like there is not yeah, basically there is a back path is not exist because the SS is unweighted plus directed. The reason behind that is directed, therefore there is a back path is not exist from a city A to city B. Let's say there is a path from city A to city B, then there is not a back path from city B to A because this is a directed case. Can we say that? Yeah, because the SS is directed, right? Now, another thing we'll look here is that, okay, fine, my SS is directed, fine. And but it is unweighted, right? Yeah. And if you look at the one path, if you look at any general path here, then in every path, can we say that I am required to like visit every node? Okay. So the length of path should always be same. Yeah, that is the number of edges. If I look, the length of path is always be your n minus 1 edges. Can we say that? Yeah. So the path length will be same. That is always equal to n minus 1 edges, right? Exactly. And another thing is that that is the one thing. And I need to like the weight of the s if you consider, then the weight of s is also same. Can we say that? As it is given, it is an undirected graph. So weight of each is exactly same. So if I apply the concept of Hamiltonian path, then the path in which all the weight is are same, or all the like whatever the s we are traveling, all the weights of that s is same, and we are visiting all node exactly once. So can we say that all the paths are identical? Exactly. That is the reason behind it. Like here, all the paths is actually identical. Okay. So although in this question, they have not asked you to print the path, if they ask you to print the path, then what you need to do? We just need to, we can say that like I just print any valid path because all the path is identical. I need to print like any valid path. Yeah. And that will be our perfect answer for it. Right. So I will like take care of any valid node and I will just print it. Then that will be our the valid path, but it is not asking this question. Okay, I just need to find the number of possible combinations for it. So if I relate this problem with the traveling salesman problem, and if I look at the constraint here, look at the constraint here, that is n is lesser than or equal to 20, right? Exactly. Right. So the n is lesser than or equal to 20. This is our constraint here. If you observe this, then what could be the time complexity it can work, right? It can work for a time complexity if I look for it. Then if I look for a time complexity, then it will simply work for 2 to the power 20 into, you can say, 20. Or if I skip this, then I can say that it will work for 2 to the power n into n. Why so? Because 2 to the power n is somewhere lead you to 10 to the power 6 because 2 to the power 20, I already told you like close to 1 is 6. So it is 10 to the power 6 and n is your somewhere in the power of 10, so it will simply work for 10 to the power 7 operation, right? Yeah. So if I relate this problem with the Bitmask traveling salesman problem, then if I look the state here, then yeah, it is definitely now considered as a Bitmask DP problem, because I need to look for all combinations. So can we look for all the sub problems? So since I need to find all the sub problems, this is directly we can consider it as a Bitmask DP problem. Can we say that? Yeah. So what could be the state here? If I look at the state here, then I can say that the state is DP mask what do you call current node, right? And guys, one more thing I want to tell you, that since it is somewhere like if you look at if you want to write the transition function for this function, basically the relation between all the transitions, then that is quite vague, right? If you going to write that, then the topological dependency, if you look, that topological dependency will be quite harder. So for problems like this, where the topological dependency of subproblem like finding will not be easy, for that I generally use the memoization approach, and that will be a more valid approach, because the topological dependency, although you have obviously the stack, like whatever the stack memory occupied, like extra memory you need to give for stack, that will be occupied, right? That is fine. But the reason we follow memoization approach where the topological dependency is fine, because memoization approach will approach the random way. We don't need to like know the topological dependency of all the subproblems. Therefore, we follow memoization approach for the problem like this. So if I write the state relative to memoization approach, then it is like basically number of combination. Okay, number of combination from start to end, because I need to visit from all the nodes start to end, and basically your start is 1 and end is n. Okay, yeah, such that we have visited the subset mask. Okay, so whatever the subset this mask is, basically if the mask is, let's say, 1011. Okay, so if the mask is 1011, then it is quite possible that, okay, fine, the mask is 1011 means I have visited the node, whatever the first city I have visited, whatever the third city I have visited, but I'm not visited second city. So that is what we're telling. Number of combo from start to end, so that we visited the subset mask, and we are currently standing at current node. Can we say that? Yeah. And we are currently standing at current node. So this could be the possible state here. And if you clearly look at, then you can see that the mask is here. How many possible masks could be, right? You have n nodes. So if you need to like classify all in the bits, then the total number of masks will be 2 to the power n, and the number of nodes is n. So our complexity of 2 to the power n into n clearly comes here, and therefore this can be clearly implemented in the feasible complexity, right? So this would be the feasible solution of it. Now, if I look to the implementation part of it, so let's come to the implementation part of it. Okay, yeah. So let's take the input here. Yeah. Then here it is. Right. Yeah. And test case is very well one only, so it's perfectly set. Now, if I take the inputs here, then question's telling that I need to take the number of cities and flights in the first line, and then I need to take the M lines describing the flights. Basically, can we say that this is the edge list is given? Yeah, the detail of edge is given. Okay, fine. So let's take the input. Okay. Yeah. Now we have like let's consider that we are making the adjacency list, because the graph is directed. Adjacency matrix cannot be made because it will be very sparse, right? Yeah, and the weight is also 1, so we don't need that, right? So we'll look for the adjacency list here. So let's make the adjacency list here. Okay, yeah. And the total nodes will be obviously n. So the size we declaring for adjacency list is n. Now we are iterating over all the s's to take it, the input, right? And let's say that this is the start of the S, that is U, and the end of the S is V. So we'll take the input for it. And since the graph is directed, so only edge from U to V exists. Therefore, we'll put the V as the neighbor of U. Can we say that? Yeah. Showing that there is a S from U to V exists, right? Yeah. Now, guys, as we decided already that we need to use here the TSP format, but instead of finding the distance, I need to find the combination as we already cleared in state. So we need to obviously use the DP here, and obviously it will form the same format or basically follow the same format of TSP. But only thing is that instead of finding the minimum distance, we will look for the number of possible combinations. So if I try to write the TSP generic implementation, looking at the like this state where we need to find the combination, then what is the things we need to take? Let's make a TSP class here. Okay, yeah, that's a one. So the first thing TSP takes is number of n, that is the number of nodes. Then visited all. What is this? This is the mask representing all the nodes that's visited. Okay? Yeah. So if all the nodes become visited, we'll do it as visited all, right? Now, another thing we need to take care of it is here the what do you call, guys? What do you call adjacency list, right? So that is the one part of TSP. And another thing we need to look here is that the memoization table. Can we see that? Yeah. Memoization table is basically the state as we already discussed. That is the mask current node, as we already told here. What is that? Here. Number of combination from start to end. So start we visited subset mask, and we are currently a start node. So this is the memoization table to keep track of it. We'll write that, right? And apart from this, here in this question, we are not allowed to find the path, or we are not asked to find the path. But if we are asked to find the path, we'll try to see that also. How can we find the path here? Okay. And the best part is that I don't need to track like any path, as we already discussed here, any valid path is valid. So we just need to track that whether the next node is not going to be the best node like a standard TSP. We just need to take care that is it the any valid next node is there or not. So any valid next will take care of this only. But look at this, guys. There is a catch here. If I try to declare this vector, then look at this. This is a 2D vector, right? Yeah. And the mask is going for the length of 2 to the power n. And how many 2 to the power n is there? It's like 10 to the power 6. So it's like I am declaring the 10 to the power 6 container that is allocating on heap. So obviously it will cause the crash, right? It will somewhere lead to MLE, because we know that on the heap we can maximum declare 10 to the power 5. And obviously this will extra size we are declaring in current node also. So to not cause any kind of MLE, it's better to use static arrays instead of this as a global thing, right? Instead of using this 10 to the power 6 whatever we say dynamic arrays allocating on heap, we will use the static array that will safely allocate 10 to the power 6 like in general we know that 10 to the power 7 up to 10 to the power 7 we can declare globally a static array. So we can use that so that we don't get any kind of MLE or TLE, whatever you say. MLE will be feasibly possible, but TLE can be the more general way we can get, because to declare the 10 to the power 6 array, we need to visit the heap, and that cost will be more than 10 to the power 8 operation. So usually we get TLE. So to avoid that, that is the reason we are using the approach to declare it as a static array globally instead of locally. So let's do that. Okay. And one more thing, guys, although we are declaring it as long, and here the time complexity is fine, and space complexity is also fine, that is 512 MB. But if this space complexity is 256 MB and the modulo operation is 10 to the power 9 plus 7, so we don't require to like visit 10 to the power 9 plus 7. We don't require to use long here because it is perfectly coming in. So if the memory limit they cleverly put it as 256 MB, we going to write the or use long, then it will falter this and will cross the limit of 256 MB. In that case, we get MLE. So here it does not cause although any problem. We can safely use that here, right? We can simply use the long also to store overall value, and it will not cause any kind of MLE, right? So if I assign the memo here globally, then that will come out as what is the size of memo, guys? We know that it is like 2 to the power 20, so we just do that. Okay. And obviously, another thing we need to keep track is that the size of node is 20 only. So that we assign. Okay. And apart from this, any valid next will always same, like for a particular state, whatever the mask, we need to find the any valid next node. And that will also be going to be of similar size. So we just declare that because any valid next will be what? Any valid next mask and current node. So basically, what is the best next node? Not only the best next node. I literally saying I am again iterating. We are not saying that we did need the best next node. We just need to look for that whether the path we are following is valid or not. So whether the next node we are getting is valid or not, because here all paths is identical. So when I take the best next node or even I take the any valid next node, it will going to give me ultimately the same path, right? So to keep track of this, I am again declaring as a static arrays globally. Okay, yeah. So that is the one part of it. Now, if I need to initialize, and although, yeah, look at this also. Since the one is int and we are using long, so we should use LL so that it convert in long because one is by default in, so it will falter or it will get overflown because it is of 32-bit and the long is 64-bit, so it will only allow bit manipulation up to 32-bit. Although here it does not cause because we are doing the bit manipulation up to 20 bits. Look at this. We are performing the write set up to 20-bit. But if it is more than that, if it is more than 32-bit, we get overflow. So to keep track of this, that is a safe way that we use long. We convert the one to long one. Okay. Yeah. Now, if we try to initialize the TSP, so we are given what? We are given with the adjacency list here. So we'll just give that adjacency list here. Okay. So that's what we are given. Right. Now, so whatever the size of this, well, how many nodes is there? Whatever the adjacency list size is that, because for n nodes, adjacency list size will be n. Like basically storing all the neighbors details or all the else details of neighbor from a node to it, right? Yeah. And if I mark it that all the node is visited, then in which case all the nodes is visited. When I like to the power n minus 1, if I mark the all the nodes is to the power n, and if I subtract 1, I'll say that all the nodes is visited, right? Yeah. And obviously the adjacency is your adjacency, right? Yeah, fine. So like to not cause any error, it's fine. Yeah, it's fine. Okay. Now better that what is saying? You are using memo. I need to initialize this. How are you going to initialize this? That is the point here. Okay. Because we know that memo can be initialized using the fill, or it can be initialized using the memset. And since I need to like initialize the memo to be -1 so that the state is not node and any valid next also -1, so we can simply use memset because memset use byte by byte operation. So if I use it like what do you say? If I use it for -1, it will not cause any problem. It will set each byte to be 111. So overall entire byte of 8 byte of like whatever our long will be of 8 byte. So entire 64 bit will set to 11111, and we'll ultimately get it as -1. So we can safely perform memset here to initialize the memo. So what is given the format? The pointer to the array, that is memo. Now the value there we are assigning, and we are giving the size of whatever the byte we needed. It is like the best thing that it automatically calculate. Yeah, that is the advantage in the memo. I don't need to give the size explicitly. It automatically calculate. And similarly, if we need to initialize the any valid next, here also I initialize it at -1, stating that only that the next node is not known. So that is a one part of it. So size of like this will come out as any valid next. Can we say that? Yeah. So this is the one part of it because the initialization of it. Now, if we go to calculate the state here, okay. So that is what, guys. If we are looking for DP, that is we are calculating a particular state. So we will give the mask, right? Yeah, and the current node here. So if I check the base case here, then what could be the base case, guys? Base case is that it is always given that we should always end at city n, right? Or for a zero base index, I can say that I should always end at city n-1 because that is explicitly given in the problem. If we look at here, person is telling that I should always end at lemala, and lemala is city n, and for zero base it is n-1. So our ending of a path should need to be always what do you call n-1 city. Guys, if my current node is basically become n-1, so that I'm at the last node, and because it's a zero base index, obviously it should be n-1. And I need to check that does I visited all the nodes. If I visited all the nodes, then my path will be a valid path, and it will be considered as one combination of it, right? So if my mask is equal to visited all, then can we say that it is a safe path? I'll just return one. Yeah, so because it's a valid path, it will add the one combination to it. Else, it's not a possible path. So I'll just return 0 so that it will not cause any change in state or any change in number of possible combination, right? Yeah. Now another thing we look for is that memoization cache check. Okay. Yeah. Another thing we look for is that memoization cache check. So what is the memoization cache check, guys? If my state is already known, then it's a general, right? If my state is already known, then return the state. And this is the reason, right, that avoid memoization to become recursive exponential. Okay, and it will save its time complexity. So if the state is already known, just return the state, right? That is one thing, guys. Now if I look for option loop, okay, what is the options here? Here we are not allowed to like visit all the nodes, right? Because for a particular node, we are not checking that whether that there is existence of node or not. Because in general, if I look for general TSP problem, there we deliberately check because like that is given as an adjacency list, not basically adjacency list. They're given as adjacency matrix. So it might possible or it is feasible that there is a is from every node to other. So that's why there we iterate from all the nodes, but here that is not the possibility, right? Because it is directed and we have explicitly told that there is a certain number of SS is there on adjacency list. So we'll just iterate all the neighbors for the current node, and to iterate that, we'll just need the what do you say, guys? Neighbor and adjacency, what do you call current node? Yeah. So this is our explicit number of what do you call neighbors, right? Or what do you call number of options we have? Yeah. We don't need to iterate over all the S's. This is amount of S's is there. The maximum amount of S's will be this only because the matrix is sparse. Okay. It's not a filled matrix, so this will save my complexity here. Okay. Yeah. So if I look at this, then you can say that the first thing comes in my mind is that pruning check. What is a pruning check, guys? Is my node is already, or is my neighbor is already visited? Okay. If my neighbor is already visited, why you're visiting, right? Yeah, because it might possible you already visited the mask, you already calculated the it's whatever the optimal thing is there. So do not apply the duplicate calculation. To avoid that, we check that is my neighbor is already visited. So for that, we just follow the general approach. This mask at the rate 1 and whatever the neighbor bit. If this bit is not equal to 0, means my neighbor is visited, I'll just continue. Can we say that, guys? Yeah, just continue to the next one. Skip it. Right. Yeah. Now, another thing, guys, that is your now the generic. What is a generic way to calculate memoization? Here, mutation I need to do because to move to the next mask, obviously I need to perform mutation. And what is the next mask here, guys? That is basically whatever the mask I given, I'll just set the bit for the current node, right? Yeah. So I'll set the bit for the current node for the mask, and basically what is my current node? That is neighbor, right? Yeah. So if this is set, my neighbor is marked visited. That is what we are avoiding in this step. So we are visiting for this neighbor, right? Yeah. And that's why we mutate to the next one. So if I need to find the number of valid ways here, let's say the number of valid ways, and I overall need to find all the combination here. So to keep track of this, let's say the comb is there, initially assigned to 0. So that's saying that initial number of combination is 0. So if I need to find the number of valid ways for this possibility, then it will come out as what? What it come out? It will come out as for this neighbor. Yeah, we're not finding for other neighbor. We're finding for this neighbor, that whether the neighbor have like combination also or not, because it might possible the neighbor does not have combination, right? In that case, even we add, and if we try to like update the path and any valid next, then that node is not be the, what do you call, that node is not valid, right? Because the path is not valid, the combination is not valid. How can I update the valid next node, right? So to keep track of this, we explicitly finding that how many valid ways for this like next mask would be there. So we'll just check for the next mask. Okay. And what is the next node, guys? That is your neighbor. Okay. Yeah. So if I just add in the combination, that will find whatever is 0 also does not make any sense. I'll just whatever the combination it get, we'll just simply add it, right? Yeah. But here, one more thing, I cannot directly add. Question is explicitly taken that I need to find the modulo m. So I just add the valid base and I'll take the modulo m here. Okay. Yeah. Now, if I need to like check whether that our next node is valid or not, that will only possible if valid weight is greater than 0. Basically, it means that there is a combination of path exists for the next mark. Whatever the mutating we have done, there is the possible combination exists, right? So for that to occur, we can now update my any valid next node, and that will be what? Any valid next node for our current node is your simply neighbor. Can we say that? Yeah. And if you find that, it's fine. Okay. And basically, because I need to find any valid next node, so if it might possible our like these things will be valid for multiple nodes, right? Yeah. So it might possible that my next node is what you call already found. So to keep track of this, to update basically neighbor or whatever the valid next node, what do we do, guys? We just make sure that whether it is already found or not. If it is already found, then there is no need to do. So we'll just check that whether the any valid next of the current node and whatever the mask it is, yeah, is equal to -1 or not. If it is equal to -1, then you should update, as it means that it's already calculated, right? Yeah. Now, so this is the calculation for the, what do you call, any valid next, right? Yeah. So this is already happened. The memoization check is happened. The base case is happened. Means we have calculated the number of possible combinations. So what is the last thing left, guys? Just we need to update the cache and return, right? So let's just update the cache. Okay. So what is the cache here? That is memo that we need to find. Whatever the mask we are looking for, and whatever the current node we are looking for, and the number of possible combinations, right? And just we'll just update that and return back. Okay. Yeah. And in this way, we have calculated the all the states. Can we see that? Yeah. Now, fine. We have calculated all the states. Let's say I need to print the part also here. So to print the path, I explicitly told you that I'll explain how to print the path here. So if to print the path here, let's say we are looking for, let's name it as find path. Okay. And obviously we need to give the start node. In Hamiltonian path, all the start node will be like give the same path. We can start from anywhere. So we'll consider by default 0. Okay. Yeah. And to keep track of path, we'll just write vector ll path, storing in a container. So what is my current node, guys? That is your start node. Yeah. And what is my current mask here? We'll set the bit for my current node. Okay. Or whatever my start node, we'll just set the bit for it. Okay. Now until we reach the end, right? Until we traverse all the nodes, it is only possible if my current node is not equal to -1. If it becomes -1, it's traverse all the nodes, because by default value will be initialized as -1. So there will be a moment come when my valid next node is not there. In that case, I'll say that my path is ended, right? Yeah. So in general, I'll just push the whatever the node current node in the path. So that is what we're doing. We're just pushing that. Now, what is this, guys? We need to traverse to the next node. Okay. So we'll check that whether the valid next node is there or not, right? Yeah. So whatever the any valid node, that is your any valid next we stored for the, like in this container. Okay. That is your, what do you call, current mask. Yeah. And current node. It might possibility that this valid next node is not existing. Okay. Yeah. It might possible this valid next node is not existing. Then it means that my path has broken. Yeah. So if my path is broken, then just break it, right? Yeah. If it's broken, then just break. That's what we do. Else, we will update our path and traverse to the next one. So current node, your become is your any valid node. Now what is your current mask? That will be basically set to whatever, like whatever the bit representing to the this node, any valid next node. So we'll just set that bit, and yeah, it's fine, right? So in this way, we calculated all the paths for it, right? So we safely return the path. Okay. So yeah, in this way we have calculated our TSP calculation. If I come for the general calculation for it, because we already calculated the TSP here, so I need to first make the object for the TSP, right? And that is, we just pass the adjacency list here, right? Yeah. And here the input is given 1 base, and I make the TSP for 0 base. So I obviously need to convert the S's to be 0 based, right? So that's what we're doing, right? Yeah. Now that what will be the total combination, right? We are starting at node 0, right? So what will be the mask like a setting node 0? Basically whatever the mask is there, in that the node 0 bit is set. So That's what we're doing. The initial mask is the only mask in which the only node 0 is set. Can we say that? Yeah, that's what we've done. And our start node, what is there? That's 0. So it will give me all the combination for it, right? Yeah, because it's we implemented using memoization, we'll calculate using the top-down approach. We're able to get all the combination. And since we already found all the combinations, so what's my thing is that just print the number of combinations. That's it, right? So if I try to run this, let's try to run this. Okay. Oh, there's an error here. The DP was declared in the scope. Okay. And it is private. Okay. So, okay, fine. DP was not declared in the scope. Oh, this is the mistake we did. In the class, by default, we know it's private. So we need to explicitly told that whatever external thing we are accessing outside class, that needs to be public to be defined. And one more error, we need to explicitly told that this adjoint of the class we are initializing so that we don't get any conflict in the name. And now if I try to run this, then let's look at this. Yeah. DP was not declared. Yeah, so we need to call by object, obviously. Yeah. Now if you try to run this, it will possibly give the answer. Yeah, it will give the answer.